Next we have hemostasis, which is a stoppage of bleeding. So once you get a leak, how are you going to stop it? Both are aided by a vasospasming, as I mentioned before. The release upon injury is serotonin, which causes muscles nearby, smooth muscles, to constrict. That will make the blood vessels smaller, less blood goes through, so you lose less. Now remember about smooth muscles, two things to remember is they are weak and they are involuntary, so you don't have to think about this. However, since they're weak, that muscle contraction tends to last about 30 minutes. A little rule of thumb. Why this is so important is if you have a patient that's bleeding out, keep in mind at the beginning, shortly after injury, they're going to be bleeding out more slowly. Once this 30 minutes hits about there, those smooth muscles now will tire and they will relax, and if your patient hasn't bled out already, they're going to start bleeding out a lot faster. So the race is on a course always to get the bleeding to stop as soon as possible, but it can get worse. So something to keep in mind. Now there's two ways that you basically stop bleeding. Whether they're small little leaks like in the capillaries, you will use a platelet plug. This uses those platelets, the thrombocytes. Now what happens here, as we can see here progressively, remember we haven't talked about the pipes yet, but the capillaries, remember the smallest ones where red blood cells actually go through usually one at a time. They're lined with epithelial tissue and a little bit of connective tissue holding them together on the outside of that. If you tear one of these, the platelets in here will see that connective tissue for the first time. They will react to that. They'll release serotonin, which will cause muscles to constrict upstream, lessening blood flow through the area. But also they will shoot out sticky little protein barbs that will stick to the collagen on the outside and also stick to other platelets. So as they start building up here on the edge, they will now form in the middle and they will plug up the leak like a little dam. And that's okay for the little ones, because where this one might have been broken, there'll be lots. Remember, some estimated 95% of your blood vessels are actually capillaries going through tissues to allow for the delivery of water, oxygen, nutrients, and picking up waste, carbon dioxide, etc. And so you can tear some of these and other ones will be there still delivering oxygen, nutrients, and picking up waste and carbon dioxide. These tissues, of course, will grow, they will heal, macrophages will chew up the little dam, and the blood flow will continue later on. Now that works okay for platelets, but for a large blood vessel, you don't want to dam it up. That would be bad. Like up in your thigh, your leg would be lacking oxygen if your femoral artery suddenly clogged up because of a leak. And so of course you would lose your leg. So what we need to do here is make a blood clot, which is basically a patch. We want to patch the leak, not plug up the whole blood vessel. There's two mechanisms that trigger this. It's like a catch-22. You want to make certain. Now a lot of times this is due to tissue damage. Cells will rupture around the blood vessel. They'll be damaged, whether they get cut by a knife, a gunshot, but just tear. They will release a factor called tissue thromboplastin, but also cells surrounding the blood vessel will store up lots of calcium. So there'll be a calcium rush into the bloodstream. In your bloodstream always is one of those minor blood proteins. We talked about the three major ones before. Remember, albumin, globulin, and fibrinogen. Here's one of the minor ones, prothrombin activator. Less than 1%, produced by the liver. Always in there, in a small amount. But it's inactive. Its cofactor is actually calcium. Calcium levels are somewhat low in your bloodstream. And suddenly there's a rush in that local area because of this damage. And now it joins the prothrombin activator and turns it on. Now prothrombin activator will now change prothrombin, another minor blood protein produced by the liver, always in there. It will change it now to thrombin. Basically, prothrombin activator is an enzyme that turns on and chops prothrombin. And when it chops off a little extra part, it now forms into the active thrombin, which again is an enzyme. This will change that fibrinogen. Remember 4%, that precursor molecule, it chops it in half. And the one half is a sticky protein called fibrin. The sticky protein, as it goes out with the blood leaking out, will stick to the edge of the leak, the break, the blood vessel. Sticks to that, and it'll stick to another one, starts making this little string and a webbing from one part of the leak to the other. And it will catch other fibrins, red blood cells, white blood cells, platelets, and it starts forming this patch. And it'll patch up the leak. And on top of this, we add another level because thrombin can actually change other prothrombins into thrombin as well. Now this is what we call, like last semester in AP1 when we had the non-steroid mechanism. Remember we called that an amplification or a magnification effect? We're using enzymes in here in a series because once we turn on prothrombin activator, we don't make one thrombin, we're going to make thousands of thrombins. Every thrombin doesn't make one fibrin, it's going to make thousands of fibrins. So 1,000 to 1,000, that's 1,000,000, and add in this little loop also, and so we get, for about every prothrombin activator we turn on, we get some 10 million fibrin fibers. So this magnifies it. We have to do this because enzymes are quick acting. We don't want these forming downstream. We need these to form at the leak and very quickly. So as the blood is gushing out through the leak, it's going to form this patch. Now, how big of a patch do you need? Is it a small leak or a big leak? Because if it's a big leak and you make a small patch, that's not going to do you any good. It's still going to leak. If it's a small one, you make a big patch, that can be bad because part of that patch can break off, go downstream, and plug up. It can dam up the blood vessel and cause you lots of problems. Especially if that reaches your heart, your lung, your brain, you can have a stroke or die. So, as my professor used to say, you got to see the beauty in the design. The beauty of design here is it's already in there. If you have a little leak, you have a little bit of damage to a blood vessel, you'll have a little bit of activator being released. Tissue thromboplastin and calcium will activate a little bit of the activator, and they'll be magnified up, and you'll get a small patch. If you have a big leak, you're going to have a lot of damage, and that will now activate even more, and you get a big patch. So if it works well, the proportionality is already built into it, so it should work just right. Most of the time it does. And we can see diagrammatically how this works. Now the other way is called intrinsic, and sometimes the cell doesn't have to rupture. Cells can actually separate. Remember, we have those different factors that help to hold cells together, but sometimes those just come apart and you cleanly break between cells. That would not allow for that process up above to go. But we still see that we need to close this leak off. And so in those rare cases, whenever our mechanism attaches to foreign antigens, in other words, that's going to be that collagen it normally doesn't see on the outside. Similar to how the thrombocytes worked. They're going to release the calcium, and then the whole process, the main part of it, starts and will form a patch again. Notice that this part is one of your essays on this exam. I don't want you to repeat this down. It's an essay, which means basically for a 5-point essay you should write 5 sentences. In 5 sentences you want to describe this. Not just put it down like I have here. Okay, you want to write that out. And since you know the essay ahead of time, you can practice writing it out and get it into 5 sentences, and so you can memorize it and understand it, and of course get your 5 out of 5 on your essay. The fate of blood clots: fibroblasts will repair the connective tissue, as I already said. Macrophages will eat up any debris. Prevention of unneeded blood clots. Normally you don't want your blood to clot unless you have a leak. The inside lining of the blood vessel has a negative charge. Most of your proteins and such floating around have also a negative charge, and so they repel one another so they don't plaque up on the lining of the blood vessel. Prostaglandin I2 also prevents adhesion of particles to your blood vessels. And of course, heparin is also an inhibitor, in other words, a clot inhibitor, to keep everything flowing. Of course, those will be overwhelmed, and your blood clot will stop once the fusion of various factors like the calcium gets back to normal, and of course also the anticoagulating agents get back up to their normal levels to stop any kind of coagulation. Terminology: an abnormal blood clot is called a thrombus. That one I told you that can break free and wander through the blood vessels, that's called an embolus. And if it's blocking, if it gets caught in a smaller blood vessel downstream and causes an unwanted or unneeded blood clot, it's called an embolism.